Swayam Prabha. Digital India. Educated India.
Dear friends, a very good day and welcome back to another session on systems engineering. In the last few classes we discussed about the requirement analysis of engineering systems, originating requirements development and functional decomposition. We found that using the requirement analysis and the originating requirements document, it is possible for us to identify the functions required in a system, or from the top level function we will be able to decompose these functions into small functions or the smallest functions and then prepare a functional hierarchy for the system. The next logical step is basically to go for the design of physical system. So this is basically developing a physical architecture for the system, where we try to convert these functional blocks into physical elements. We will try to see how we can identify corresponding physical elements for the function, or how do we do a mapping of the functions to physical elements which will satisfy the functional requirements of the system. So in this chapter of physical architecture development, we will try to look at the functional decomposition and then the conversion of this functional decomposition into a physical architecture of the system. As we saw in the previous lectures, out of the 6 functions of the design process, we have completed the system level design problem and the system functional architecture development, and the next task is basically the system physical architecture development. To explain the importance of physical architecture development, I will just explain a case study basically of a real incident where the failures in the physical architecture development led to the failure. So using this case study, I will emphasize the importance of physical architecture. It is not only the customer requirement functions, but other functions like fault tolerance and identifying the physical components for fault tolerance plays a vital role in the system development, and this case study is a perfect example to show that how the physical architecture development overlooked the importance of having a fault tolerant system and how this led to the failure of a important system, especially an aircraft. So this actually is a case study from an aircraft in Iowa. The United aircraft 232, which was a 3-engine aircraft, it crashed on 1989 while making an emergency landing after losing one of the 3 engines, and in this case 110 people died and 185 survived. And most of you know, most of the aircrafts are designed with a lot of fault tolerant system, and in spite of all these, aircraft failed. As I mentioned, it was a 3-engine aircraft, and even if 1 engine fails or 2 engine fails, it is possible to bring the aircraft to do a safe landing, and the pilots are being trained to overcome these failures in the system, and there are sufficient fault tolerance in the system to overcome such emergencies. What actually happened here was the fan disc of the engine at the fuselage separated from the engine and crashed through the tail. So that was the immediate cause for the failure. The fan disc of the engine separated and it crashed through the tail of the aircraft. But that 1 engine failure was not at all a problem, because 2 engines were quite sufficient to make a safe landing, but the aircraft stabilization system failed to control the descent rate. So what actually led to the crash was the stabilization system failed. But how the engine failure caused a stabilization failure was an important aspect of the system design, or when we look at the system design, we will see that it is not only necessary to look at the individual system, we need to look at the overall system and then see what are the possibilities of failure and analyze it. So here even with the 2 engine, the system stabilization system failed. So how did it happen was, there were 3 redundant hydraulic systems, each powered by a unique engine, which were available for aircraft stabilization. So there were 3 hydraulic systems. So you can see that it was a redundancy in the system. 1 hydraulic system is sufficient to stabilization, and there were 3 hydraulic systems each one covered by separately by each engine. So even if one engine fails and one hydraulic system failed, there were a lot of redundancies available, and it was possible to still control the aircraft. But these 3 redundant hydraulic systems could not stabilize the system, because the 3 hydraulic systems converged at the location near the tail where the fan disc ripped out, the single point of failure for all the hydraulic system. So the point where all the hydraulic system outputs were converging at one location, and the fan disc exactly ripped at that point and blocked the hydraulic system. That was the cause, because even though all the 3 hydraulic systems were working perfectly, and there were 2 engines powering the hydraulic system, the hydraulic power supply could not reach the control plane actuation points, because this was a single point where all the 3 hydraulic system converged to give the supply. So this was a single point failure in the system, and this is one of the important points to look at when we provide the fault tolerant system. We need to avoid the single point failures and then make enough redundancy in the physical architecture to make sure that such single point failures do not occur in the system. So the physical architecture development is very important, or it actually plays a vital role in identifying such situations and then eliminating the possible causes of failure. So in this case, the pre-existing fracture on the surface of the fan disc was identified as the main cause of engine failure. So that was the main cause, because the fan disc had some problem, but the design flaw of single point failure resulted in the aircraft crash. The main reason why the aircraft crash was the single point where all the hydraulic systems were converging, and from that point onwards it was a single point failure situation. So this was the reason why actually it resulted. So in the architecture development, we will look at the fault tolerant systems, and then how do we provide the necessary redundancies in the system to avoid this kind of failures of engineering systems. So let us look at the physical architecture development from the logical step forward from the functional architecture. So as we progress, we will look at the redundancies, and then how do we provide the physical systems to have sufficient redundancies in the system and avoid such single point failures. So here let us discuss about the physical architecture and what is physical architecture. So physical architecture of a system is a hierarchical description of the resources that comprise the system. So basically we look at the physical resources which actually provide the functions in the system. So architecture is basically we write down the hierarchical structure describing each physical resource or the physical element which provides the necessary functions in the system. The hierarchy begins with the system and the system's top level components and progresses towards down to the configuration items. So we start with the top level component or the top level assemblies or sub assemblies, and then we move towards the sub assemblies and components, and finally to the configuration items. Configuration items are basically the software, hardware, or a combination of software and hardware, people, facilities, or documents. So any of these could be a configuration item. So we will list down all these items in a hierarchical fashion and then complete the physical architecture. So in the physical architecture, by looking at the physical architecture, we will be able to tell what are the components being used there, what are the assemblies, what are the sub assemblies, and what are the other items which actually comes as configuration items in terms of people, facilities, as well as the documentation. And then we will be able to identify, okay, which are these components provide the functions, or which function is mapped to the particular component, or which are the components which provide multiple functions, or which are the multiple functions satisfied by a single component. All these things you will be able to identify from the physical architecture. So it provides resources for every function identified in the functional architecture. So that is the basic idea. We have the functional architecture, and from the functional architecture we will try to identify the resources for every function. And how do we develop this physical architecture? It actually starts with the functional architecture. As I mentioned, it is a logical step next to the after developing the functional architecture. So we develop a very generic physical architecture from the functional architecture. So generic physical architecture is basically a conversion of the functions into components, but we do not identify the exact component here, we just write the generic name or the generic way of representing that function in terms of a component. So, that is the generic physical architecture without giving any details of the components used. And then from that generic physical architecture, in order to get the physical elements, we create a morphological box for alternative physical elements. We will discuss about this in detail, how do we do the morphological box or how do we develop the alternatives, but morphological box is a tool for developing the alternatives for physical components. So, we identify one generic component in the generic physical architecture, and then we develop or we identify all the generic components and then develop morphological box for these components, where we will have many alternatives for that component and then choose the component. So, that is the use of morphological box, where we have alternative physical elements, and then using these alternative physical elements we will generate the alternative instantiated architecture. So, instantiated architecture is basically an architecture, a physical architecture, where we identify the component and then write down the component instead of the generic physical name of the component. So, here it is more specific, and that is why it is known as instantiated architecture. And from this instantiated architecture we will be having many choices for here, and then based on our requirement we will select a suitable physical architecture. So, we go through these steps. We will start with a generic physical architecture, and then we go for a morphological box to identify the alternatives, and using the morphological box we develop an instantiated physical architecture, and using the instantiated architecture we will identify a desired physical architecture for the system. So, that is the process, and the exit criteria, or when we decide or how do we choose a physical architecture, is basically the provision of a single physical architecture that is satisfactory in terms of detail, quantity and quality for development. So, we look at the many possible options in the instantiated physical architecture and then see whether it actually satisfies in detail, in quantity and quality of the development requirement, because this has to be developed and we need to make the system. So, we look at the details of the instantiated physical architecture and then see whether the quality and quantity are actually matching with the requirement, and once it is satisfied I will go for that particular architecture and choose the physical architecture for the system. So, that is how we develop the physical architecture of a system. So, this is explained using the IDEF0 diagram or different process. So, as you can see here, so this is the first level. Well, we do the brainstorming and select a generic physical architecture. So, in this generic physical architecture, of course, we need to do a little bit of brainstorming here, because from the functional architecture to convert the functional architecture to a generic physical architecture it is a bit tricky and requires a lot of discussions and understanding of the functions, and then finding out the generic elements for the generic architecture. So, we need to do bit of brainstorming. So, the team members will sit together and then look at the functional architecture and then see how do we convert that into a physical architecture. So, for this the input will be the system level functional architecture, and then the system level operational concept will be used in identifying the generic physical elements. So, these are the two inputs, and then we will be using these inputs, and that will be used in the brainstorming session, and we will be getting a generic physical architecture here. And this generic physical architecture along with the input from the system level function architecture will be used for generating the morphological box for alternate instantiated physical architectures. As I mentioned, the morphological box will give you the alternative elements for the generic elements identified in the generic architecture, and using the morphological box we can actually have alternate instantiated physical architecture, and from there we can actually use these inputs from the instantiated physical architecture, and of course we will be using the input requirements, as I mean the operational concept as well as the functional architecture, and then the requirements we will be using selecting the alternate instantiated physical architecture which actually satisfy the requirement of the system, and that actually gives you the system level physical architecture. And there will be many candidate physical architectures based on the instantiated physical architecture, and the choice, as I mentioned, it depends on the quantity, quality and the practical the feasibility of implementation and developing the system. So, this is the general process of developing the physical architecture. As you can see, there will be many interactions and inputs and output between these, and whenever there are some changes, it will go back and then get changed in the physical architecture, generic architecture, as well as the instantiated physical architecture. We will go through a few iterations to make sure that we are actually reaching a stage where we can choose one architecture for development. So, that is the way how the physical architecture development is happening. So, let us go into the details of how we actually develop this. As I mentioned, the generic physical architecture is a description of the partitioned elements of the physical architecture without any specification of the performance characteristics of the physical resources that comprise each element. So, here we actually partition the elements. As from the functional architecture, we identify the elements and then partition them and write down them as in a hierarchical way, similar to the functional hierarchy. So, using the functional hierarchy, we will develop a physical hierarchy of the elements, but in this case we will not give any performance characteristics of the physical resources. So, it will be more like very generic names. So, no performance specifications will be mentioned in the architecture. So, that is the generic physical architecture. So, it actually provides common designators for physical resources in a hierarchical decomposition. So, it is more like a very common or general designator for the elements. So, no specific component will be identified. So, no specific physical systems are identified here in the generic physical architecture. So, this is basically as a starting step for the physical architecture. So, converting the functional architecture to a generic physical architecture by giving the generic names for these components without specifying their performance or the physical element used in the architecture. So, that is the generic physical architecture. So, as you can see, this we have seen in the previous lectures. So, this is the functional architecture. In the functional architecture, we write down the top level function and then the sub functions, and then we decompose them into many levels depending on the requirement, and the lower level functions will be identified, and most of the time these lower level functions are the configuration items which will be identified in the generic architecture. And from this functional architecture, we convert that into a generic architecture. This actually shows the functional architecture which actually we saw in the previous lectures also. So, this is the from this functional architecture we develop the next level of physical architecture. So, as an example, I can show you this is the functional architecture for an elevator system, and we saw that this is the top level function where move passenger between floors and then accept passenger request and provide feedback and control elevator cars. These are the sub functions. Using functional decomposition, we identified how to get these functions, and from there we can actually decompose them into further, like provide input output interface, process data, provide control commands, etc. So, this way we can actually develop. Now, when we convert this into a physical architecture, then we can see that the physical architecture can actually be, or a generic physical architecture will be more like a direct conversion of the functions into generic components. So, here you can see that the top level component in terms of the generic architecture is the elevator system. So, the provide elevator services is the function, and elevator system becomes the generic component which will provide this one. Similarly, provide input output interface for the passengers is the one of the functions, and here the passenger interface component becomes the generic element. Similarly, elevator car or shaft component becomes the generic element for the next function. Similarly, control elevator cars, the control component becomes the generic element, and maintenance and self test component becomes the generic element for maintenance functions. So, again we have not specified any specific control component or the elevator car or the type of interface here. So, we just converted the function to a generic physical element, and same way we can actually divide this component or this assembly to sub components like elevator call announcement component, car control component, and destination control, door control, emergency control. Then car component, this is a cab component, interior door component, ventilation and lighting component, like this. Shaft structure components, exit component controls, shaft switch component, floor stop component, leveling component, drive brake. Then here itself you can again decompose into normal drive, emergency braking, like this. So, what we are trying to do here is to convert the functions or the functional block into the generic names or generic components. So, the here without any specification of the car component or the control component or the braking component or ventilating component, we are simply writing down this as a generic name like interior door component or the ventilating and lighting component. So, what should be this particular element, what should be the specification of this will be decided in the next level. So, the first level is basically identifying the generic names or generic components and then writing down them in the functional in the same as functional hierarchy or in a similar way of functional hierarchy and getting the generic physical architecture. So, this is the way how we get the generic physical architecture. So, starting with the functional hierarchy, we convert the functional elements in the functional hierarchy to generic elements and write down them in the hierarchical way, then you are getting the generic physical architecture. So, from this onwards we will be going to the next level where we try to identify the components for each of these elements. So, here we have not specified the element. So, next level we will try to identify the elements for these components. So, this is another way of representing the hierarchy generic architecture. Here again this is for the aircraft component. Here again we do not specify the particular elements here, but we will give a generic name for this like crew command devices, crew command sensors, central controller, aircraft device sensors, actuator controller, then actuator, then aircraft devices, actuator controller and actuator. So, this is the way we write down the generic physical architecture. We do not specify what kind of a sensor we are using or what kind of an actuator we are using and what kind of controller we are using. We simply specify the generic name of those elements, and from based on this then we will go to the level where we can identify few actuators and then choose one of the actuator for this, replace this with the actual actuator we are using or the actual component, then we are getting the next architecture, which is the instantiated architecture. So, in order to get the component names, we need to do a brainstorming and then try to find out what are the possible options for these elements, and this is done through the this is actually the same figure, previous figure explained in detail here or more for better clarity. So, you can see the control the generic names of these elements written over here. So, to get the instantiated physical architecture, which actually is architecture to which complete definitions of the performance characteristics of the physical resources have been added. So, we will take the physical architecture or the generic physical architecture and then we add the names of the components to these elements, and then that gives us an instantiated physical architecture. So, this can be done by mapping the functions to components and then doing and checking whether the components actually satisfy these functions. So, we can do different kinds of mapping of functions, and it is known as the one-to-one mapping or one-to mapping. There are different ways of mapping. This one we will see in detail in the and we allocate the architecture. So, this for the time being you can understand that this is basically used to identify whether all the functions are being mapped to components or how these components are mapped to the functions, whether there is a one-to-one or one-to mapping, or there are functions which actually satisfy multiple components which actually satisfy multiple functions, or there are some functions which have been left out without any components. So, these things can be identified using this kind of mapping functions. So, instantiated architecture, what we try to do is to identify the components for the physical elements and then write down these elements with the architecture or the generic physical architecture. So, when we add the actual physical component to the generic physical architecture, we are getting the instantiated physical architecture. So, to do this we need to go for the morphological box. Basically we take the physical architecture, we do a mapping and then we get the instantiated architecture. So, this mapping, in order to do the mapping we need to generate the alternatives. So, we generate the alternatives through the mechanism called morphological box. So, we use a morphological box to get the components and then we do a mapping of this component with the generic elements and then we get the instantiated physical architecture. We will see how to get the mapping. Basically we will develop the morphological box initially. So, morphological box will be developed to get the alternatives and then they will be mapped. As you can see here, a morphological box is a matrix representing the components of the generic architecture and the alternative choices for fulfilling that generic component. So this is basically a matrix of alternatives for generic components. In the generic physical architecture, we develop the elements, generic elements, and then based on these generic elements we can identify all the alternatives possible and write down them in a matrix format. We are getting the morphological box. So this actually divides a problem into segments and posits several solutions for a segment. So we can actually divide the whole problem into small segments, and then each segment can be analyzed separately, and we can get alternatives for each of these segments using morphological box. So this is an example for a morphological box. If you look at the how the morphological box are developed. So this is an example for a very simple product called a hammer. So if you take a hammer as a product, and then how do we develop the morphological box for this product? We look at the generic components and the generic requirements like a handle. So if you take the handle as a product, then we can see that handle size and handle material, then striking element, weight of hammer head, and nail removal element as the generic components in this case. So these are the generic elements, and we need to develop the alternatives for these generic elements. So we can actually write down the possibilities here. So alternatives are, you can have a handle size of 8 inches or 22 inches, and we can have different handle materials, fiberglass with rubber grip, graphite with rubber grip, or steel with rubber grip, steel I-beam encased in plastic with rubber grip, or wood. So these are the possible options for the handle material. So this is the alternatives for handle material, and for striking element we can have alternatives like a 1 inch diameter flat steel, 1 inch diameter grooved steel, or 1.25 inch diameter flat steel, or a 1.25 inch diameter grooved steel. Similarly, the weight of the hammer head can be 12, 16, 20 or 24, and nail removal element could be a steel claw at nearly a straight angle, steel claw at 60-degree angle with handle. So these are the alternatives possible for a particular system, I mean particular product. So this is just to explain the morphological box. In actual system design you will be having much more complex alternatives, much more complex structure, because we will be having many generic elements, and then we need to have many options. And here this is a simple product, that is why you see only few options given here, but even with these few options or few alternatives, it becomes very difficult to choose a particular product, because particular configuration, because you need to look at the alternative options here and then the implications of them in actually selecting the alternatives. So here you can see these are the options from the architecture. If you look at the morphological box, you can see that there are 2 options over here, there are 2 options here, and you have 5 options in handle material, and another 4 options in hammer head, and then the striking feature again 4 options. So how do we actually, if you want to make one hammer, so what should be the possible combinations here? So that actually to be chosen by the design team based on the requirement and the customer expectations, as well as the customer needs identified and the initial concept. Based on that they need to choose a particular combination from here. But there are some combinations which are not possible, and such combinations will be added with a line or connected with a line. So in that case we will actually eliminate those combinations, because of some reasons this 22 inches and an angle combination don't work. Similarly this 22 inches and wood won't work because of the again implication, the design implications. So such situations can be easily marked, and then we can eliminate them, and then the remaining can be considered for choosing the alternatives. So this is how we use the morphological box, or we develop the morphological box for a generic element or multiple generic elements, and then develop the alternatives. This actually shows with more clarity. As you can see, these are the different options for handle and nail removal feature, then striking feature, similarly the weight of hammer head. So you can create this kind of graphical representation of also from the morphological box, and then develop or choose the alternatives depending on the requirements. But some of the points to be noted or to be taken care of while developing the morphological box is that there should be at least one column in the morphological box for each generic component in the generic architecture. So we have many generic components, and at least one column in the morphological box for each generic component should be there. So then only we can actually develop the alternative. So for every generic component we should identify the alternative. So the meaning of this particular statement is that every generic component should be having many alternatives, or at least a few alternatives should be identified for generic components. And there is no requirement that each generic component have the same number of columns. So it is not necessary that there should be same number of alternatives for every generic component. So we can have in some cases can have 2 alternatives, or some cases we can have multiple alternatives, or 5 or 6 alternatives can be, because depending on the generic component we will be able to identify 2 or more alternatives. So there is no rule that there should be equal number of alternatives in the case of generic components. Then generating creative alternatives for generic components recommended. So always it is recommended to have innovative alternatives instead of going for the known and already existing. So it should be always advisable to go for creative solutions. So instead of choosing a ready-made or a readily available component, if you are really interested in making a product or a system which is different from the existing one, and you want to make it a little bit more innovative, then it is advisable to go for creative solutions for alternatives. So this actually helps us to identify the possible options and to apply our creativity to get alternatives and make the system much more simple and innovative compared to the existing system. So always try to go for creative solutions for alternatives. And in some situations more than one choice could be selected for a single instantiated architecture. So this is again saying that when you have multiple choices, it is not compulsory that you choose only one choice for that particular architecture. There is a possibility that you can have multiple choices for a particular generic element, and then add this as possible options, so that at a later stage if you want to add more features or you want to increase the features in the product, they can be easily added to that one. For example, if you want to have some peripheral devices for a computer, so you can actually have multiple options there. Which one to be added can be decided at a later stage, or we can actually have options for adding this at a later stage. Therefore we can have peripheral devices as a generic element. You can have speakers, then USBs, or printers, scanners, and camera. All those can be added as alternatives in the instantiated physical architecture, so that this actually becomes part of the instantiated architecture instead of choosing a single product or a single element as from the morphological box. So some situations you may like to have more choices in the instantiated physical architecture. So let us look at the one example where how do we develop this instantiated architecture, basically from the morphological box. So this actually shows an automobile navigation support system. This actually gives a better clarity. You can see here there are many generic elements here. This is basically a system for automobile navigation support. Suppose you have a car and you have a navigation system in the car, and what are the generic elements in that navigation system, and then how do we convert these elements into physical elements will be the question here, and to do that we will develop the morphological box. So here you can see direction support is one generic element, localization is another generic element, and then processor, then user input outputs, and other interfaces. So these are the generic elements in the architecture, or in the generic physical architecture we will identify these elements without specifying the actual product. Then we can see that what are the options for direction support. Here this is the morphological box for the navigation support. So for direction support we can see you can use a map and a database. It is a very simple, you can use map and database, or you can use map, database, and a routing algorithm. Along with the map and a database we can have a routing algorithm, and then we can have a staffed control center where the navigation support can be directly provided to the driver, or you can have an automated control center. So these are the options for direction support. So in order to support the driver for the directions, we can use any one of these options. And what this symbol shows here are the possible manufacturers or commercially available system. So here you can see that this shows the Acura navigation system, then BMW or Oldsmobile Curtstar, then Cadillacs or Lincolns and Redkey. These are the commercially available in the market. So this actually shows that for this particular one we can use any one of these. So we are more like specifying the details of that particular component in terms of the commercially available product. So once you say that okay, out of these 4 any one can be chosen, so indirectly I am making the specification of this particular component. So from the generic name we are going more to the actual physical element here. Similarly, the staffed control center, these 2 operators who provide the staffed control center, so any one of these can be used for this particular application. So for this generic element of direction support we have many options, we have identified 5 options and we have identified few real physical components also. So any one of these can be selected. Similarly, for localization we can decide not to have a localization, or we can have a direction sensor for localization, and you can have electro gyros or GPS transponder or a full GPS support. So in order to get the localization, so if you do not want localization we can actually decide okay, the driver can himself decide where he is, or he can identify the location, or we can have some direction sensors to look at the directions and then decide where the location is, or you can have gyroscopes or GPS transponder and full GPS support. So any one of these methods can be used for localization of the car. And then again we are specifying if it is available commercially, we are giving the choices also here. So any one of these can be decided or chosen for this particular. Suppose the decides to go for GPS transponder, so he has 4 options and out of this he can choose the one which he wants to have. So the specification, once we choose a particular component, the specifications are fixed, so no need to worry about the component details here because it is already existing. And the same way we can go for other generic elements like processor. You can have a processor in the vehicle processor can be used, or a separate 32-bit processor can be used, or a portable PC can be used. So any of these options are possible for a processor. And the user input output, you can have a regular cell phone or a special phone for this, or a dedicated phone for this, or we can have a display, LCD display 4-inch or 6-inch, or a display with a touch screen, or a button and a key panel, joystick, control knob, voice output. So there are multiple options for the user input output interface. And the last one basically you have other interfaces. You can have some interfaces with the system, or you can decide not to have any interface with the system, basically other system interfaces, or you can have an interface with the horn or light, or you can have interface with car door locks, emergency signal and airbag. This is basically to help the customer or the driver to contact the services, emergency service provider. So you can actually link the passenger navigation support system with an emergency system, so that this becomes an additional interface. Again there are multiple options, you can actually connect it with the horn lights or car door or emergency signal. So you can see here we identified few generic components, and for these generic components developed the alternatives. And as I mentioned, it is not necessary that all the generic components have equal number of alternatives. Here you can see there are variations in the alternatives, and based on these alternatives we can decide what actually should be the configuration, the physical configuration of the system. And once we select these components and then write down the physical architecture, we will get the instantiated physical architecture. So we are identifying the architecture with the components and the component specifications, so we are getting instantiated physical architecture. So this again shows another example for morphological box, and then how do we choose a particular configuration for it. So here you can see it is a manual propulsion system for a small boat. Again it is a simple example to show how to use the morphological box. So here you can see these are the design parameters or the generic elements: input motion, input source, input device, output device, mechanism and operator position. So these are the requirements or generic elements. So here you can see the input motion can be a rotating one or an oscillating one or reciprocating one are the options, and then input source will be both hands, then input device hand crank or pedals, output device fin, jet or propeller, mechanisms are gears, belts, pulleys, linkage, pump, etc. and operator position is sitting, standing, reclining or kneeling. So, these are the alternatives for the this particular feature or the generic element, and based on these generic elements we identify the alternatives, and then from there we can actually choose a particular configuration. So, in this case you can have that manual propulsion system could be based in a rotating type using both hands with a hand crank and a paddle wheel with a belt pulley and in a standing position. So, we can have a propulsion system where a operator is in standing position and it is connected through a belt pulley to a paddle wheel, and using hand crank both the hands it is being rotated and getting the manual propulsion system. So, this is how we use the morphological box for choosing a particular configuration. So, the same principle can be applied in the case of system design also. We will identify all the alternatives and then choose particular based on the requirement we choose one of these alternatives, or in some cases multiple alternatives to choose our physical structure. So, this is how we develop the physical architecture. This actually explained the same figure, the previous figure with a better clarity. So, you can see here all the options are listed here and the choices are marked with a line over here. Okay, so if you look at the elevator case study previously, we can identify few elements. So, the physical elements I just shown only 2 options here. Of course, you can have multiple options, as an example I have shown here. So, we identified that in the generic physical architecture there are an emergency component, and then there is a telephone component, a ventilation component and lighting component. So, we identified these are the generic components. Now, how do we actually choose an alternative, or how do we get the options and then instantiate the architecture? So, we will write down the emergency component as audio alarm. Okay, you can give the make over here, or you can have a visual display, another make, or in the telephone you can have a wireless phone or a push button kind of phone, terrestrial or a mobile, this is a mobile phone or a terrestrial phone with a push button. We can again define the manufacturer and the make, so it will be very specific to that particular product. And you can the ventilation component, we can have a centralized air conditioning for all the cars, or you can have a simple exhaust fan connected to the elevator room. So, then again you can specify the model or what the size specification can be given clearly here. Then you have the lighting component, you can have a fluorescent lamp or a LED lamp, and based on the requirement we can choose any one of these and then write down the component name. In the generic physical architecture, if you write down the audio alarm as an emergency component, then it becomes an instantiated architecture. So, like this, if you write down the component name and the specification for the each and every generic component, then the whole architecture becomes the instantiated physical architecture. And there are the different ways of representing the architecture. So, this is the generic structure, and in terms of a block diagram. So, we have the hierarchical way of representation as well as the block diagram way of representation. So, hierarchical way we already saw in the functional architecture how it is done. In the block diagram we write down the generic architecture and then we write down the name of the component adjacent to this, then it becomes a instantiated physical architecture block diagram way of representing. Okay, that is the way how we develop the instantiated physical architecture. And when we develop this architecture, there are different issues to be taken care of, but is basically the functional performance. So, we make sure that the physical architecture we do a proper mapping of the components to the functions. So, the functional performance need to be taken care of and then made sure that we identify the required functions and the components needed for this, and then other things like the availability and other utilities and the reliabilities, all those things to be taken care of, and then we need to provide the components for those functions also. And then the future growth potential and adaptability to be taken care of. We need to ensure that there is sufficient potential for the growth, and then the cost of the whole product also to be taken care of. So, in next lecture basically we will try to see how to take care of these features, basically the reliability of the system or the fault tolerance of the system, and how do we provide the components, physical components to give these functionalities in the system. In the previous structure we looked at the from the functional architecture we developed the generic physical architecture, and then from generic physical architecture we try to develop the alternatives and then instantiated physical architecture. In order to complete the physical architecture, we need to add the other features like fault tolerance and other aspects of the system, and once you add the components or we identify the alternatives for such functionalities, and we then add these components to the system, then only the complete architecture will be developed. So in the next lecture we look at the possibilities of adding the fault tolerance and the alternatives for fault tolerant functions, and identify the components for fault tolerant functions and add these components into the physical architecture in order to complete the instantiated physical architecture. So we will discuss all these points in the next class. Till then, goodbye.